Davison-Germer experiment, electron diffraction. Initial atomic models proposed by scientists could only explain the particle nature of the electrons, but failed to explain the properties of related to their wave nature. C.J. Davison and L.H. Germer in the year 1927 carried out an experiment popularly known as Davison-Germer's experiment to explain the wave nature of the electrons through electron diffraction. In this article, we will learn about the observations and conclusions of the experiment. Setup of Davison-Germer experiment as like this. The experimental arrangement of the Davison-Germer's experiment is discussed below. An electron gun comprising of a tungsten filament F was coated with barium oxide and heated through a low voltage power supply. While applying the suitable potential from a high voltage power supply, the electron gun emits electrons which were again accelerated to a particular velocity. In cylinder perforated with fine holes along the axis, these emitted electrons were made to pass through it, thus producing a fine collimated beam. The beam produced from the cylinder is again made up of fall on the surface a nickel crystal. Due to this, the electrons are scattered in various directions. The beam of electrons produced has certain amount of intensity which is measured by the electron detector, and after it connected to a sensitive galvanometer and to record the current is moved on a circular scale. By moving the detector on the circular scale different positions that are changing the angle theta, angle between the incident and scattered electron beams, the intensity of the scattered electron beam is measured for the different values of angle of scattering. Observations of Davison-Germer experiment. From this experiment, we can derive the below observations. We obtain the various of the intensity I and the scattered electron by changing the angle of scattering theta. By changing the accelerating potential difference and accelerating voltage was varied from 44 voltage to 68 voltage. What the intensity of the scattered electron for an accelerating voltage 54 volts at a scattering angle 50 degree centigrade could be strong peak intensity. Thus, a peak was the resultant of the constructive interference of the electrons and the scattered from the different layers of the regular spaced atoms of the crystal. With the help of the electron diffraction, the wavelength of the matches was calculated to be 0.165 nanometers. The correlation between the Davison and Germer experiment as follows: lambda is equal to h by p, and a wavelength of associated with the electrons, that is 1.27227 by square root of 54. Galvanometer. Electron conductor. Tungsten filament.
Along its axis, producing a fine collimated beam. This collimated beam is directed to fall on the surface of a nickel crystal. The electrons are scattered in various directions by the atoms of the crystal. The intensity of the electron beam scattered in a given direction is measured by the electron detector or the movable collector. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam is measured for different values of angle of scattering.
Electron detector.
Theta, which is the angle between the incident and the scattered electron beams. This experiment was performed by varying the accelerating voltage from 44 volt to 68 volt.
48, 58,
It
or
was noticed
64,
that a strong
68.
peak appeared in the intensity
Volts.
I of the
Peak
scattered
intensity
electrons
54
at
volts.
an accelerating voltage of 54 volt and at a scattering angle theta equal to 50 degrees. The appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regularly spaced atoms of the crystal. From electron diffraction measurements, the wavelength of an electron is denoted by lambda was found to be 0.165 nanometers. We know that the de Broglie wavelength of an electron is denoted by lambda is equal to h by p, where h is Planck's constant and p is the momentum of the electron. if the electron is accelerated from rest through a potential difference of V volt. Then, substituting the values of mass of the electron, charge of the electron, and Planck's constant, the expression for wavelength is obtained as 1.227 by square root of V nanometer. In this experiment for diffraction of electrons,
from electron diffraction measurements
at 54
0.165 nanometers.
On substituting this value in the equation and simplifying, we get the associated wavelength equal to 0.167 nanometer. This theoretical value is in agreement with the experimentally obtained value of de Broglie's wavelength for electrons. The Davison-Jemmer experiment thus confirms the wave nature of electrons and the validity of de Broglie relation. The de Broglie hypothesis has been the cornerstone of many advancements and applications in recent times.
Aim of the experiment: to demonstrate the diffraction phenomena of electron to support wave character of the material. Okay. This experiment gave establishment of quantum mechanics and the Schrödinger wave equation. Setup, experimental setup. Electron gun, electron detector, incident beam, scattered beam, and the metal target of the crystal nickel. The experiment consisting of a firing electron beam from the electron gun directed to a piece of nickel crystal at a normal incident that is perpendicular to the surface of the crystal. The experimental included an electron gun consisting of a heated filament that released thermally excited electrons, which were then accelerated through a potential difference, giving them as a certain amount of kinetic energy towards the nickel crystal. To avoid the collisions of the electrons with other molecules of their way towards the surface, the experimental was conducted in vacuum chamber to measure the number of the electrons that were scattered in the different angles. An electron detector that could be moved on a arc path about the crystal used the detector was designed to be accepted only.